Okay. All right, so today we're going to start talking about our independent and dependent events. So far we've been talking about geometric probability, where we said this was some desired region over some total region, whether that was a shaded portion or a piece of some given figure. Today we're going to be talking about independent and dependent events. So this is actually going to be set up in a fraction in the same way, some desired portion out of total, but there will be two events happening. And you're supposed to be determining, does that second event get affected by the first event or not? So if it does not, then we are dealing with an independent event. So this is what you're going to write in the definition blank up there at the top for independent. So our independent is the outcome from one action does not affect the probability or the outcome of some subsequent activity. So this means whatever happens first doesn't change anything about what's going to happen for your second event. Okay, and this could happen in three ways. So I think there's a list below, 1, 2, 3. So the first would be that your two events are completely unrelated. Like maybe your first event is that you're going to go over to the snack bar and pick a snack, and then you're going to go over to the vending machine and get a drink, right? Those have nothing to do with each other. They're completely separate. The second would be that maybe you're repeating an event whose numbers don't change. So it's the example of like spinning a spinner on a game or rolling a dice. Whenever you roll a dice, you have the same chance of rolling that number again the second time, right? Nothing changes about it. You didn't take anything away from that dice. Just because you rolled a 6 the first time doesn't mean you can't roll a 6 the next time, right? You have the same chance of that happening either time. The third way that this could happen is if whatever you're doing gets replaced. So maybe there's a bag of candy, and it has a few different color or flavors of candy on the inside of the bag. Say you pick one, right? But then you put it back, and then the next person picks. Okay, that means that there's still the same total number of candies inside of the bag. Okay, and the formula that we use for finding independent probability, which again is the ones where event 2 is not affected by event 1, is the probability of A and then B is found by multiplying your probability of A times the probability of B. So again, this is our formula for independent events, which means these two events are independent of one another. They don't affect each other's outcome. All right, so once we have this formula written down here at the bottom of the page, we're going to look at an example of an independent event. Okay. All right, so this event here, it says, suppose you spin each one of these two spinners. What is the probability of spinning an even number and then spinning a vowel? All right, so as we can see, these spinners have different pieces on each, right? This one's got numbers, this one's got letters. So it says that in event 1, we're hoping to spin an even number. So that means we're spinning on this spinner. Okay, what are the chances of spinning an even number on this spinner? 1/2, right? There are 3 even numbers out of a total of 6 spaces. So you have a 3 out of 6 chance, which does simplify down to 1/2. Good. All right, then event 2 has to do with spinning a vowel on this second spinner. Well, what's the chance of that happening? 1/5, right? This one has 5 sections, so the probability of spinning a vowel is 1 out of 5. Then they want to know what's the probability of these two events happening. Okay, so then we follow that formula that we just wrote down. Probability of event A times probability of event B. Well, this was our probability from event 1. This is our probability from event 2. So our formula says we would just multiply those two together to get the probability of that outcome for both events. So it would be 1/10. Remember, we multiply numerators and denominators. Bless you. All right, so there's an example of an independent event. So now let's talk about our dependent. So our definition for dependent is that this is the outcome from one action that will affect the probability of the outcome of some subsequent action. So this is what you'll copy onto those first set of lines there. And then it says, in other words, for that portion, you'll type what's after the blue here. So this means that the result of the second event is going to change because of whatever happened in your first event. So maybe going back to that example I gave earlier, where you have a bag of candy, and let's say I reach in and I take out a red candy, and then Elizabeth goes to take out a piece of candy. Since I've taken one of the red ones, she has a changed probability from what I had of getting a red candy, right? There's not as many red in the bag, and there's also not as many candies total in the bag to choose from, right? So her probability would be different than mine because it wasn't replaced. There's less in there. Okay, so that means that our formula is going to change just a little bit. Because these two events are not completely separate events, our formula will be the probability of A and then B is probability of A times the probability of B after A. So we can't write these two fractions separately like we did on that last example. We're going to have to consider whatever happens in A before writing the fraction for whatever happens in event B. All right, so now we're going to look at an example of a dependent event. So again, dependent meaning whatever happens for event 2 is changed because of whatever happened in our first event. All right, so our example for dependent is that there are 6 black pens and 8 blue pens in a jar. If you take a pen without looking and then take another pen without replacing the first, what is the probability that you will get 2 black pens? All right, so let's start with drawing a black first. So the first person who goes and draws a pen has all of the pens in the jar, right? None have been taken out. So how many pens are there total? 14. And they said that we were looking for the probability of them drawing a black pen. So out of the 14, how many were black pens? 6. So the probability of drawing a black the first time, when all the pens are in there, is going to be 6 out of 14, right? Which will simplify to 3/7. But they said you do not replace that pen and you go draw another one. Well, now there's not 14 pens in the jar, right? How many are there now? 13, right? And we still are hoping to draw a black. How many black are in the jar? 5, because we didn't replace the one we drew the first time. So the probability of event B, the total changed and the number of black pens changed. And now we multiply these two fractions together to find out the probability of drawing a black pen both times. So I'll be multiplying my 3/7 times my 5/13. Again, remember we're multiplying numerators and denominators. So in the numerator, I've got 3 times 5. In the denominator, 7 times 13. We end up with 15/91. Okay, On the next section, I am going to display a few scenarios up here on the board, and you are going to determine if you think that that describes an independent event or a dependent event. So here are the 4 scenarios. There should be a number 1, 2, 3, 4 blank for you there. You're just going to write in the blank if you think that scenario is independent or dependent. And I'll read them to you if you're having trouble reading it. So number 1 says, you pick the letter Q from a bag containing all the letters of the alphabet. You do not put the Q back in the bag before you pick another tile. Take a second. Do you think that's independent or dependent? All right, number 2. You have a bag of marbles, 3 blue, 5 white, and 12 red. You choose 1 marble out of the bag, look at it, and then put it back. Then you choose another marble. Independent or dependent? Number 3, you have a basket of socks. You need to find the probability of pulling out a black sock and its matching black sock without putting the first sock back. Okay, and then the last one says tossing 2 dice and getting a 6 on both of them. Okay, so what did you guys think about number 1? Independent or dependent? Dependent. All right. What about number 2? Nice. And number 3? Good. And number 4? Good. All right, so now that we can identify which they are, let's look at a couple more examples. All right, so here they ask you to find the probability of taking a jack out of this deck of cards and a factor of 12 on the spinner. So first of all, what do you guys think? Is this independent or dependent? Independent, right? These two have nothing to do with each other, right? This one's cards, that one's a spinner. Good. Okay, so how many cards do we have here? 5. And how many of them are a jack? Okay, so the probability of a jack would be 1/5. Good. All right, so it is independent, and a jack is 1/5. All right, on the spinner, how many sections do we have? 8. And how many of those sections are a factor of 12? Yes, 5 of them. Good. So what would be our probability of drawing a jack and then spinning a factor of 12? Wait, right. We multiply numerators, we get 5, denominators 40, and that 5 over 40 will simplify down to 1/8. Very good. Oops, sorry, I didn't mean to skip it. 1/8. All right, so let's look at our next example. This one says the probability of rolling a 6 and then rolling not a 5. Okay, so first of all, independent or dependent? Independent, right. These dice do not affect, or are not affected by whatever you roll the first time. Good. Okay, so how many sides do the dice have? 6, so what's the probability of rolling a 6? 1/6. Okay, and then for their second event, they want to roll anything but a 5. 5/6, right. There's 5 other sides they could potentially roll, which gives us a probability of 5 over 36. Nice. Okay. All right. Okay, here they want the probability of drawing a queen and then a queen. It says all of the letters of the alphabet are in a bag at one time. Do not replace the letter. Okay, so the first event, oh, not a queen, sorry, a Q and a Q. I was still stuck on our cards. All right, all the letters of the alphabet are in a bag, and you're not going to replace the letter after you've drawn. All right, so if we're talking about all the letters in the alphabet, how many are there? 26. How many of those letters are a Q? 1. So the probability of drawing a queen the first time is, sorry, I didn't ask you that, dependent, right? Is 1 out of 26. Okay? And it says we're not going to replace it. So if I don't put that Q back in, how many numbers are there in the bag? Letters are there in the bag? 25. And how many Q's are there? 0. So the probability of that happening is 0 out of 25. So when I multiply those together, what's the probability of this event happening? 0. And this one is a dependent, right? Because we did not replace what we drew the first time.